Hello friends, welcome to the lecture series on design and analysis of algorithms. Today I will discuss asymptotic notations. This is Sahil Shah from VPKBIET Baramati presenting lectures on design and analysis of algorithms. Today's topic is asymptotic notations. To start with, any algorithm is a step-by-step sequence of instructions which are used to accomplish a goal. So for running any algorithm, we must consider two factors, namely space complexity and time complexity. Nowadays, considering cheaper availability of hardware resources, the space complexity will not have a much weightage in comparison with time complexity. So our main focus should be on minimizing the time complexity of any algorithm. Basically, complexity of an algorithm specifies the number of resources required for successful execution of an algorithm in order to arrive at a desired solution. So a programmer's goal will be to design an algorithm which minimizes time as well as space complexity. So which are the factors that are coming under computation of time complexity? One must be aware that we are having normally in any program or algorithm two types of instructions or programming statements. The basic instructions, also known as primitive expressions. These are the simple or straightforward instructions which makes use of primitive arithmetic operations, like you are observing P is equal to Q plus R upon 2, S is equal to P minus 3. All these are requiring a constant time for their execution. Next type of instruction is use of control loops. We can make use of while, do while or for loop for repetitive execution of same statements. For example, suppose we are writing an algorithm for computing factorial of input number n, then there will be three stages involved in computation of factorial. Step number 1, assign a value 1 to a variable fact equal to 1. Then I am running a for loop with value of I from 1 to n, and we are recomputing value of factorial in each iteration using a formula fact is equal to fact multiplied by I. So what will be the overall time complexity, time required for execution of this programming construct? So for execution of this program, we will require a total time of execution as 2 times time required for assignment. A question may arise, why 2 times? Here there are 2 assignment operations in our program. Initially we are assigning a value of 1 to fact variable, and inside a for loop at the first iteration we are assigning value 1 to variable I. After this assignment we are making comparison of value of I with value of n. So those n comparisons will require a time of n plus the time required for increment operation, time required for actual multiplication, and time required for assignment. This will contribute in deciding overall time required for factorial of the number. Moving forward, there should be consideration of few of the operators which act as dominating operators over the other. As we can see in this example, the time required for assignment, time required for increment is much smaller in comparison with time required for comparison of I with n, as well as time required for this multiplication. So in our factorial program, multiplication will dominate all the other constant or assignment operations. While deciding a time complexity of any algorithm, main focus is given on the operators which are dominating the smaller constants or assignments. Majorly, there are 2 categories of programs or algorithms. Algorithm can be iterative, where there is usage of simple assignment, primitive expressions and control loops, and second category of algorithm could be recursive algorithm or recursive program. So how time complexity is computed in both the cases? If our programs are of iterative type, we will focus on number of times a particular loop iterates. So that will dominate all the other statements present in iterative program. As we can see an example, while computing factorial of a number, the main focus was on number of comparisons made before entering or taking an exit from a loop. In case of recursive program, we would be interested in how many recursive calls are made in order to arrive at a final conclusion. Let's say we are having a program of computing factorial of a number using recursion, and I am interested in finding factorial of 3. How would I find factorial of 3? Factorial of 3 will be equal to 3 into factorial of 2, which is in turn equal to 3 into 2 into factorial of 1. As factorial of 1 is a base case, this factorial of 1 will return a value as 1, which will in turn return a value to fact of 2, and fact of 2 will give us the value to fact of 3. That means fact of 3 is dependent on 2 recursive calls, namely fact of 2 and fact of 1. So total number of recursive calls involved in any recursive program will contribute in deciding final time complexity value of that operation. Moving further, there is a concept known as growth rate, also known as order of growth. What it is? Basically, whenever we are executing different algorithms, we may come across various input sizes. The performance of an algorithm based on size of input is known as growth rate. You can observe a definition. Running time of an algorithm varies with input size. This variation is known as growth rate. It is also known as order of growth. Example, suppose we are having a linear time algorithm, let us say linear search, with the input size n as 5. So I will require 5 comparisons for checking out if a number is present in a list of 5 integers. As the size grows, let us say we are having 100 integers, I will require a constant amount of time nearly equal with 100 units of time. So as input size grows, we will have growth in the running time of an algorithm. This terminology is known as growth rate or order of growth. This growth rate indicates how quality time required by any algorithm varies with the size of input. Based on this growth rate, we are having a classification of our algorithms into various efficiency classes. Several classes exist. Out of them, prominent classes have been discussed. First efficiency class is a constant. This type of class will have all the algorithms or problems which are requiring constant amount of time for execution. You can observe efficiency class is a constant. The growth rate is 1 or k. These algorithms will require constant amount of time for execution. Examples of such types: addition, multiplication, division, subtraction, all sort of primitive operations, removal of largest or smallest number from max or min heap respectively, or if I am carrying out addition or deletion of new element, existing element from a stack or queue, that is push, pop, NQ, DQ operations will require a constant amount of time. Next category of efficiency class is logarithmic. This will require a log to the base 2n amount of time for execution. Examples: binary search, or if we are interested in either inserting or deleting an element from a existing binary search tree. As we can observe, in case of binary search tree, the searching is halved between two parts, left as well as right. So the time required will be half of n, that is represented as log to the base 2n. At every level, the time goes on reducing. The third category of efficiency classes is linear, wherein we are requiring big O of n time for execution. The famous examples where linear amount of time is linear, n is denoting the size of input. As size of input grows, data and complexity will grow. Examples: insertion or deletion of a node from linked list, linear search, finding out max or mean from array of integers. Next category of efficiency classes: linear plus logarithmic. This will be represented by ordering function and log n. The examples are merge sort, heap sort, and quick sort. We are having one more famous category of efficiency classes known as quadratic. This will require n square amount of time for execution. The famous examples: all sorting algorithms like bubble sort, selection sort, insertion sort will require a quadratic amount of time for execution. Moreover, the operations on two-dimensional matrices like addition, subtraction will require this n square amount of time for execution. Moving further, the next category of efficiency class is cubic, where we are requiring n cube amount of time for execution of an algorithm. The example: finding out transitive closure of a binary relation using Warshall's algorithm. Second, we can perhaps use this n cube in case of matrix multiplication, where there is usage of 3 for loops. Next, the efficiency class can be exponential if it is requiring 2 raised to n growth rate. The examples: finding out power set from an existing set, knowing optimal solution for a given 0-1 knapsack problem using dynamic programming, so on and so forth. The final category of efficiency classes is finding factorial. It's kind of factorial. This will have order of growth as n factorial. The famous example in this case is Hamiltonian cycle, checking out if the given graph contains Hamiltonian cycle, travel insertion problem using brute force approach, finding out permutations, combinatorics. All these will require n factorial amount of time. Revising the efficiency classes we have seen so far, we are having total 8 major categories of efficiency classes. Namely, we are starting from constant. It will require 1 or k amount of time. All basic primitive operations will be covered under this. Then comes logarithmic for binary searching or either insertion, deletion of an element in binary search tree. We will require log to the base 2n. Then comes linear. We will be requiring an amount of time for execution of such problems in efficiency class linear. The famous problems are finding out max or mean element from a list of integers, checking out if a number is present in an array, and so on and so forth. Next category, linear plus logarithmic. It is represented by n log n. Examples: merge sort, heap sort, and quick sort. Then we are having fifth category of efficiency class as n square. This is known as quadratic category. All sorting algorithms come under this category. Then comes cubic for matrix multiplication. If we are obtaining running time as n cube, it will require a cubic efficiency class. Next efficiency class is exponential, where we are requiring 2 raised to n amount of time for execution of a problem or algorithm involved in this. Examples: power set or finding out optimal solution using dynamic programming for a 0-1 knapsack problem. The final category of efficiency class is factorial of a number, which will be represented by symbol n factorial. The example: finding out whether a graph possesses Hamiltonian cycle is a famous example in the category of factorial efficiency class. Let's have a look in between relationship of all these efficiency classes. As you can see in this box, the constant is the least time complexity. So we are using a general notion of O. O of 1 is lesser than O of log raised to kn, which is lesser than O of log n, lesser than O of log n. O of log n is lesser than big O of log n raised to k, which in turn is lesser than big O of n. It is lesser than big O of n log raised to k, and it is lesser than big O of n log n. It is lesser than n square. lesser than n cube is lesser than 2 raised to n, and n factorial is the highest or greatest limiting class which restricts running time of any algorithm which is known till date. Users are advised to carefully observe this box which is depicting a relationship between various efficiency classes. These concepts are really useful while understanding the notion of asymptotic notations, which is the point of discussion for next session. Moving further, what do you mean by asymptotic notation? So asymptotic notation is a mathematical tool that is used to find time or space complexity of any algorithm without actually implementing it in a programming language. One may say asymptotic notation acts as a symbol or mathematical expression that is used to represent time or space complexity of any algorithm. Remember, we are not actually implementing a program corresponding to an algorithm. Based on known assumptions, we are finding out limiting behavior of that program or algorithm. So without execution, we will come to know about time complexity or space complexity of a particular algorithm. Example, let us say I want to check if a particular student has finished assignment or not. Without checking out his or her notebook, I cannot directly say that a particular student XYZ has completed an assignment or not, because based on some past behavior or limiting behavior of that student, I come to deduce the present behavior of that student. This is nothing other than using an asymptotic notation. In the similar manner, while deciding time complexity of any algorithm, we will use such a symbolic representation to denote asymptotic notation of an algorithm. This asymptotic notation will majorly focus on major terms or statements which affects overall cost of a particular algorithm. As I already said, any asymptotic notation is independent of all machine specific instructions or constants. As we will not have actual implementation, there will not be any role of machine specific instructions. So how one can stress on focusing major terms or statements in a program? Example, searching or sorting. We are interested in comparing an element with existing element, so comparison will dominate all the other operations or assignments, if any, in that searching or sorting program. In case of factorial, multiplication will play a primitive role and all the others can be dominated by multiplication. In the similar notes, while finding out maximum or minimum element in an array of integers, I will be mostly interested in comparing one number with the other. So comparison plays a vital role. This is the meaning of this. While introducing asymptotic notation, we must focus on major terms or statements that are affecting overall cost of any algorithm. So generally, asymptotic notations describe the limiting behavior of any function. Let's say f of n is equal to 8n square plus 4n minus 32. What shall be maximum time required for execution of this function? As I can see, if I increase the value of n starting from 0 towards infinity, f of n will be approximately equal with 8n square, and these 4n or 32 can be assumed as constants or minor terms, and we should focus on this major term 8n square. So I can conclude growth of function f of n is limited by n square. So n square acts as a asymptotic notation for a function f of n. It is giving us the higher limit. Assumptions made while defining asymptotic notations. While having asymptotic notation for any algorithm, we will not consider actual cost of any operation like performing addition, multiplication of two numbers, assignment or anything. The more focus will be on major terms. If there are usage of any abstract or smaller cost functions, those should be simply, you can observe O of c n square can be reduced to O of n square. C is ignored. Only leading terms of a polynomial are considered, and they are being given more weightage in comparison with all non-linear smaller terms. Leading terms are given weightage. O of n cube plus n, even though I am having plus n, n cube will play a major role, so this will decide limiting behavior in comparison with n. If there are any multiplicative or divisive constants used in deciding time complexity of an algorithm, those should be skipped. You can observe big O of 4n square can be reduced to big O of n square, big O of n square upon 8 can be reduced to big O of n square, and so on. So in short, asymptotic notations are going to give us upper bound, lower bound and strictly tied bound for any algorithm in terms of running time required. Asymptotic notations can be generally classified into 5 types, namely big O notation, big omega notation, big theta notation, little o notation, little omega notation. This big O notation will give us the idea about upper bound, what can be maximum time required for executing a particular algorithm. This upper bound will be given by big O type of notation. Big omega notation will give us an idea about lower bound for a particular algorithm, lowest possible time required by an algorithm to execute. Big theta notation will give us an idea about tightest possible bound required for execution of an algorithm. Little o will give us tight upper bound, little omega will give us tight lower bound. Little theta does not exist, as big theta is the tightest possible bound. Let's see these asymptotic notations one over the other. First, big O notation, denoted using symbol big O. It defines, big O notation defines the upper bound for any algorithm. That means the running time of any algorithm will not be more than its asymptotic upper bound for any random sequence of data. I mean to say, if we consider any raw input on a specific algorithm, what shall be the maximum time required by that algorithm? This maximum limit is known as upper bound, and this is given by big O notation. Let's see it mathematically. We have two algorithms with the non-negative functions f of n and g of n. These are the two non-negative functions indicating running time of two random algorithms. We will say g of n is an upper bound of f of n if there exists some positive constant n0 and c such that 0 less than equal to f of n, which is less than equal to c of g of n for n greater than equal to n0. Remember, here n0 and c are the constants, positive constants. For these values we are getting upper bound value. In short, function f of n, algorithm represented using function f of n, will always have the time required that will be less than or equal to c of g of n. How to denote this? The big O notation is denoted using this notation, f of n equal to, we can write instead of this equal to belongs to as well. Some books are using belongs to notation. Basically it should be belongs to only. F of n is belonging to upper bound big O g of n. That means g of n will give a guideline or limiting behavior that will be maximum for an algorithm given by a function f of n. Let's see its graph. So we have plotted a growth rate of a function against input size. We can observe as value of n grows, as the size of input grows, we are having a fluctual change in c of g of n. This curve is denoting c of g of n and this one is denoting f of n. At a particular point of time, as value of n input grows, there will be a drastic growth drastic change in growth rate of C of G of n, and it will be always higher than f of n. This final point where f of n and g of n are crossing over, this point is known as n0. Beyond this value of input, we will always have f of n lying below C of G of n. You can observe as n grows larger, f of n grows slower than g of n. This final point of crossover is known as n0. You could observe these two functions are crossing over at several points, but beyond this function there is no crossing over, and that point is the starting initial value of input which is used in deciding the final upper bound of our algorithm. So what do you mean by loose upper bound and tight upper bound? Let's see. So generally a tight upper bound will be equal to a particular function, while loose upper bound will always be more than a particular function or particular efficiency class. The definition of loose upper bound: set of functions having their growth rate or order higher than actual bound. So what are the upper bounds for 6n plus 5? For 6n plus 5, 6n plus 5 is coming under linear category. So for n, I am having quadratic more, then cubic more, then exponential, that is 2 raised to n more, and n factorial more. All these are more than 6n plus 5. So all these will come under the category of upper bounds. Okay. Now upper bounds are tight upper bound and loose upper bound. If I say 6n plus 5, does it belong to big of n? Yes, 6n plus 5 belongs to big of n, but big of n is equal to 6n plus 5. And what are its higher classes? N square, n cube, 2 raised to n. So as per the definition, set of functions having their growth rate order higher than actual bound will come under the category of loose upper bounds. See the usage of the word loose. Loose means they are not strictly upper, they are something more than upper. 6n plus 5 belongs to big of n square, which belongs to big of n cube, which belongs to big of 2 raised to n. Second example, f of n equal to 3n cube plus 5. This belongs to big of 2 raised to n, which belongs to big of n factorial. What shall be incorrect bound in case of this? All set of functions with growth rate lower than actual bound of that function are called incorrect bounds of that function. As we can see, in case of big O notation, we are interested in functions with higher or equal timing requirements than that of existing function. So all those functions with the lower case timing requirements will come under incorrect bound. For a function f of n equal to 6n plus 5, n is linear, big of 1 will act as a lower, so 6n plus 5 will not be equal to big of 1, while 6n plus 5 is equal to big of 1, big of n is equal to big of n square, and so on. 3n cube plus 5 will never be equal to big of n square, which will never be equal to big of n. I hope you have understood. This big O notation is used to denote worst case time complexity of any algorithm. Example, suppose we are having a sorted list of integers and I am interested in finding out maximum element. Okay, so if our array is not sorted, if we have been provided with some random sequence of integers, the maximum number of comparisons I need to have is n, where n is size of array, in order to find the maximum element. So that will be the behavior of worst case time complexity given by big O notation. Moving further, big omega notation. This type of notation defines the lower bound of an algorithm. It means running time of an algorithm cannot be lower than its asymptotic lower bound for any random sequence of data. This is just reverse of big O notation. Here we are interested in finding out what shall be the lowest possible complexity for our algorithm. The equation for this is given like 0 less than equal to C g of n less than equal to f of n. Remember, in earlier case we were having a notion f of n was lying between 0 and c of g of n. This g of n was giving us the upper value. Now this the c of g of n is giving us the lowest possible limit. It is denoted using symbol f of n is equal to omega g of n. G of n is smaller than f of n. How it looks in a graph? You can observe after a particular crossover point, f of n will always be higher than c of g of n. It gives us lowest possible bound. So what do you mean by lower bound? It is set of functions having their growth rate lower than actual bound. Students are advised to refer big O notation one more time. You may pause this video at the intermittent times in order to have clear understanding of this topic. This omega notation is just the opposite of big O notation. In case of big O, we were interested in finding something upper more than existing. In case of omega, we are interested in finding something lower or equal to existing. So for example, if I am having f of n as 6n plus 5, what are the lower or equal classes with respect to 6n plus 5? I am having omega of n, omega of 1, all these are lower, so those are acceptable. For 3n cube plus 5, I am having omega of n cube, omega of n square, omega of n, omega of 1, and so on. All lower will come under category of big omega notation. So what will be incorrect in this notation? Set of functions which are having their growth rate higher than actual bound of that function. If I say 6n plus 5 equal to omega of n square, it will be totally invalid, because in case of omega notation, our interest is on finding out lower rate functions. Users are advised to pause this and try these examples on their own. 3n cube plus 5 will be not equal to omega of 2 raised to it will be equal to omega of 2 raised to n. Yes, no, it will not be, because this will be higher than, okay, there is mistake. This should be not equal to, okay. Moving further, this sort of notation, big omega, is used to denote best case time complexity of any algorithm. Considering again the previous example, finding out maximum number, if array is already sorted in a descending order, we can perhaps find the maximum number present at the first location in an array requiring a constant amount of time. So that will be the best case time complexity. It is generally given using asymptotic notation, big omega. The third and foremost category of asymptotic notation is big theta notation. It defines the tightest possible bound for any algorithm. It means running time of an algorithm cannot be either less than or greater than its asymptotic tight bound for any random sequence of data. Big O was giving us the upper limit, while big omega gives us the lower limit, and this big theta notation gives us equality. So you can observe mathematical notation. In case of big theta notation, running time of a particular algorithm will always be equal to, not less than, not greater than, it will always be equal to a particular asymptotic tightest bound. 0 less than equal to c1 g of n, which is less than equal to f of n, less than equal to c2 g of n, where n greater than equal to n0. So this is denoted using symbol f of n is equal to theta g of n. Whenever there is a usage of theta, that means f has to be equal with g. F will lie in between c1 g and c2 gn, where c1 and c2 are the constant. We can observe on a diagram plot of three functions fn, c1 gn and c2 gn is drawn. At this point we can observe f of n is lying in between c1 and c2, so this point acts as n0. Beyond this, there will not be any further growth in f of n more than c2, or it will neither be lesser than c1. It will always be in between c1 g of n and c2 g of n. As A theta notation defines the tightest possible bound. There will not be any notion of a loose bound. It doesn't exist for theta notation. So what will be incorrect bounds? All the set of functions with